Hi, and welcome to another edition of Ordinary Differential Equations. Today we are going to talk about application of ODEs to finance. This is going to be an example of a first order equation for modeling a financial transaction. Let's go ahead and see what the story is. So situation is something like this, that you go to a bank, you want to open an account and save money for some event in the future, let's say for your retirement. So you have certain number of years to keep your money in the account, so that would be the time or your time horizon. At the beginning you might deposit a certain lump sum. We call that S0 for initial amount. And then perhaps you decide that you will have a yearly contribution of certain number of dollars. And the bank tells you that they are willing to sign a contract and give you a certain interest rate for that period. Now, to make the problem simple, we are going to use continuous compounding so that we don't get tied down with the issues of the calendar and how many days are in a year, or how many months, if this is 30 days or 31 days and stuff like that. We are going to put those kind of issues aside. You probably take a course in engineering finance and you look at this thing in a much more detailed way. But we are going to make life simple for ourselves. We are going to just look at continuous compounding. Let S be the total money that's going to be in your account at some time t. The question is, how do we model this situation? As usual, we go ahead and take a look at the change in this quantity, the change in your total amount. There are two reasons that your money is going to change. One of them is that you are getting interest from the bank. The interest is proportional to the interest rate that you have and the total amount that you have at that moment. Another reason your account is increasing is that you're going to make a deposit. This deposit is going to be assumed to be a continuous deposit as opposed to a lump sum deposit. At any rate, the amount of the change in the account in a unit of time is going to be K dollars. And our initial amount is, well, our initial deposit. So our differential equation is ds dt is equal to rs plus k. This is the contribution from the bank. This is your contribution. Now, as we said, this kind of differential equations show up in this course very often. We might as well have the solution ready-made so that we apply it and move on quickly with our problem. So in the previous lectures, we had talked about general equation y prime is equal to ay plus b with a and b a constant and an initial condition of y0. So you can solve that with integrating factor or with separation. Either way, we have a solution for that obtained rather easily. Here, all that we pay attention to is that instead of the generic a, we have a quantity r that makes sense to us as interest rate, and the other generic quantity b here is replaced by our yearly contribution. So, and with the initial deposit S0 playing the role of Y0 over there, we can write the amount on the account quickly. So it's going to be B over A. So B over A is K over R negative plus S0 instead of Y0, and again K over R exponential of RT. So that is rather quick. Let's go ahead, apply that to a scenario. So suppose we consider your case again. You're a recent college graduate. You want to save for retirement and you're lucky to have $10,000 to your name. And you want to decide how much to set aside so that when you retire in 40 years, you're going to have $1 million to your name. Wouldn't that be great to have $1 million? The question is, how much should you set aside? and that all depends on our assumption about the prevailing interest rate. In our problem, of course, we are making simple assumption that R is a constant. In real life, that's rather hard to arrange, but let's suppose that we assume that the interest rate is perhaps 4% or 8% or 12%. For each of these cases, we want to figure out how much we have to set aside as our yearly deposit to make it to our goal of $1 million. The question is, what's the amount of deposit in each case? Instead of total deposit, let me correct this thing, and this is what's the yearly deposit. And then also we might ask what was the total deposit. Let's just separate the two questions. So in our problem, S0, our initial investment is 10,000. Our goal is to reach $1 million. Our time horizon is 40 years, and our interest rate could be any of these several numbers. So what is it that we are looking for? We are looking for how much we have to set aside for each of these scenarios. All the other quantities are given to us. So I go ahead, solve this equation for K, and plug in the numbers for different parameters of my problem and figure out what the K is going to be. You can use your calculator, or as we are advertising Desmos in this class, we go ahead and see how to use Desmos to do the exact same thing. So let's open this thing. I have S is equal to minus K over R plus S0 RT plus K over R ERT. So what I'm going to do is to take this S0 to the other side, and from these two other terms I'm going to factor my K. So I will have S minus S0 ERT is equal to, I might as well factor R as well. So I'll have K over R. From here I have exponential of RT, and from here I just have minus 1. So what I want to calculate is K. So I write it here, K cross multiplied by R. So I'll have R times numerator S minus S0 exponential of RT, and denominator is going to be well, exponential of RT minus 1. So all that is left to do is to plug in these numbers in this equation and get the K. That's how much you have to set aside yearly, and then you'll be on your way to your retirement. Okay, so it would be straightforward to put these things in a calculator and figure out what K is, but let's learn a few things about Desmos while we're at it. See what other advantages we can have out of this, essentially comparable to what your advanced calculator will do. So let's see. We go to our Desmos. I have to define that function, so and pretty much I'm going to type in what we had over there. So say K. Now I'm going to signal to Desmos that my main variable is R, and everybody else is going to be considered as a parameter. And the name for a parameter in Desmos is a slider, because it makes these sliders and then you can just play it and then get the same answer. So I'll have R on the right hand side of the equation, you remember. Then I have on the numerator I had S minus S sub 0. S to type in sub 0, you just put underscore and your letter, then exponential of well, I had to go forward one step, e to the power of is shift 6 RT, go to the right. Then I have to divide by e, again exponent RT. I right arrow to go forward and come down, then -1. So that is it was complaining that my somehow it thinks that I have a quote in my subscript. Let's see, I had a space, and that's what was causing the problem. Okay, so now I corrected it. It says, do you want slider for S, S0 and T? Well, I'll say yes. It understands that I want to treat R as my main variable. I kept R as my variable because the problem is asking you to investigate 3 different interest rates. Now, Desmos by default starts all of your parameters at 1, and that's obviously not a good number for us. The S we are after is 1,000,000, not 1, and not any of these type of numbers. S0 is also like 10,000. T is supposed to go to 40. So the standard scale is not good for us. We have to correct it. How do we correct it? You go to this end of the scale, click on that, and it gives you an option. So we click on this thing. The amount of money that you want in the future, anything from 0. We were supposed to make it to $1 million. So to make a slider go past that, maybe you go to 2 or 3 million. Let's write 3 million, 3 zeros, and then another 3 zeros. Step of how quickly do you want to go through these numbers? Well, we don't want to count dollar by dollar to go to $3 million. So I might as well make my steps to be big steps like 100,000 or something. So we want to get to our final number quickly, as opposed to taking forever to get there. S0 is our original investment. Your original investment, anything between 0. We were asking for 10,000. Let's go ahead, open this thing up. Any number above 10,000 will be okay. So for example, let's say 40,000. That's a good amount. Step of I pick a step size comparable to where I want to go. And T, our timeline to horizon, well, we want to make it to there in 40 years. So let me just say 60 here, and step of 5 is fine. Okay, I want to have $1 million, so I move forward. It shows up 100,000, 2, 3, 4, 5, 6, 7, 8, 9, and this is $1 million. Initial investment, we want to start at 10,000, so we quickly go to 10,000. Notice if you had chosen your steps smaller, you have to drag through more steps. T, I want to go to 40 years, so I go to okay, 40 years. And now we come across something that looks anticlimactic. What is this graph? I don't see much of anything here. It's just 2 lines. What does that tell me? Well, the issue with any software is that you have to be a careful user of it. You have to know exactly what you're doing, what you're looking for. It's not going to make all intelligent decisions for you. It doesn't know anything about your finance problem, what kind of numbers you're using, and so on. So there's no substitute for an intelligent user. What is the issue here? The issue is the numbers that you show in the axis are not really kind of numbers relevant to us. These are the kind of numbers you see in Algebra 1, Algebra 2. All graphs go from 1, 2, 3, and so on. Our numbers, of course, are not that kind of numbers. This is a million, that's a 10,000, and so on. So our scale is not correct. We expect our yearly deposit to have something to do with thousands of dollars, and so our K is not supposed to be like you are not expecting to deposit $2 into your account and make $1 million. That's a good dream, but maybe with a lottery ticket, but not with a financial calculation. So what do? We go ahead and we have to set our graph to some reasonable axis. So we go here. So x-axis is called x-axis, but really in our problem that's the R. So interest rates that we are investigating was 4%, 8%, 12%. So I go from 12% means 0.12. So let's go ahead and just be generous here. Let's go to 0.2, and maybe I make my picture symmetric by putting this at minus 0.2. The issue is y-axis. Y-axis that is representing your deposit. Deposit, we say, well, we suspect maybe $10,000, $1,000, something like that. Definitely is not a negative, at least shouldn't be. Typically, you're not withdrawing, you're depositing. So let's just put that some reasonable number so that we can see the bottom of our graph. On the vertical, let's go over and let's assume, for example, $10,000. You see the emergence of something. You see that previously we had a graph that looked to be going straight up, but now we see some structure there. We see the graph emerging, and I still don't see my y-intercept. 10,000 is not enough. It's still going higher up. So maybe I go ahead and make this thing say 40,000. Now I see my graph much better. So I see, let's see if you understand what the graph is. First, in this issue of learning how to draw a picture. Even if you have a software, you still have to know what's going on before you even attempt graphing. It doesn't matter if you have a calculator or what, the same issues do come up. So again, what are the axes here? On the horizontal, we have the interest rate. 0 means bank not giving you any interest at all. Well, and then what? 4% will be here, 8% will be around here. This is 10%, and 12% will be 12% will be here. So this is 11, this 12%. So let's go ahead and see what do each of these things mean. What if the bank doesn't pay you any money at all? How would you reach $1 million? So that would be peculiar for you to just put your money in a bank and they don't give you anything in return. But we are just playing a scenario at 0. 40 years, well, you need $25,000 a year to set aside so that in 4 years you will have $1 million. Now, given that at the beginning you're setting aside $10,000 at the first day, you're going to end up paying a yearly deposit a little bit less than $25,000. Let's go ahead and see what happens at 0.4. If you don't see 4 itself directly, we might as well go ahead and try to see if our calculator understands. No, perhaps it doesn't. So 4%, at 4%, I see that I have to pay this amount every year, slightly less than 10,000. Here's an easy way of actually getting that number straight out. We have defined a function here. So k of 0.04. This is telling me I have to set aside $9,617.63 aside. And then at 4% a year, I'm going to make it to $1 million. Well, what if I get a better deal of 8% a year? 8% sometimes is used as a historical average of stock market over a long period. you take it with a grain of salt, because stock market, as you see, fluctuates quite a bit. But in 40 years, maybe that's a reasonable assumption. It all depends on your point of view. So K of 0.08, we notice that when interest rate just doubled from 4% to 8%, the amount that I pay yearly reduces by a substantial amount. Almost, this is a quarter of what I was paying over there. $2,565.55 a year. That's how much you have to set aside yearly. That's almost like $7-8 a day. Quite doable if you can actually manage to have a return of 8%. What if we get super lucky and some bank gives us 12%? Ah, I see something peculiar. Negative amount. What does that mean? It means the original $10,000 that you're going to deposit by itself is going to reach $1 million and actually more. And in fact, you are allowed to withdraw as opposed to a deposit. Withdraw $214 a year, and you're still going to make it to a $1 million mark. So you see the effect of the interest rate going up is quite substantial. Notice the reverse issue that when you have when you owe a credit card a certain amount of money, the amount of interest they charge is substantially more than these things. Sometimes, if you're not careful, you could end up paying like 30%. And that's going to be rather astronomical. You want to avoid being in that kind of a debt for a long time. Yeah, and this is a good example of what happens. You can turn this problem around and calculate some problems with high interest rates and see how amount of money accumulates over time. So we have these findings. We can take it back to our table here, and so I might as well write those numbers here. So we found out for 4%, the amount of yearly deposit you had to put was almost, let me round it so that I don't crowd the screen here. This was 2,500 and some change, and at 12%, we had a fortunate situation that we could actually withdraw money and still make it to $1 million. So what's a yearly deposit in each case? That's how much we should deposit, and that was actually withdrawal. What's the total deposit? Well, total deposit will be you're making a deposit of K dollars a year for T years, and originally you set aside S0, so your total deposit, let's write here, total deposit that's the amount of cash you took with yourself and just left it in the bank. So first day you left S0, and then every year you had K dollars, but you repeat that every year all the way to the retirement day. So that's the total amount of deposit that you have. So we can go ahead for each of these, make a calculation on what this will be, and that would be our total deposit. For example, $10,000 plus 40 deposits of $2,565 a year, it makes almost like $112,600. You go ahead and calculate this one and calculate that one. What does this mean? It means over the year you have given the bank $112,000, and at the end of 40 years you withdraw $1 million. How does 100,000 become $1 million? Well, that's the power of compounding. This is when it works for you, and the opposite is if you owe money, and if the interest rate is much higher, the amount that you pay is going to be quite substantial. So I invite you to calculate that for yourself and see how you end up with some rather astronomical numbers. Okay, let's go to another type of problem that is rather common here, which is sometimes instead of you putting money into an account, you go ahead and you borrow money to buy something. Typically how you buy your car or your house or something, you make installment payments. Again, we are going to assume that we are doing continuous calculation, means instead of installment every month, you're continuously paying. That's just to make our calculation easy and not get bogged down with calendar and the issue of series calculation. That's going to be another topic we don't want to get into. So we are taking from the point of view of continuous compounding, and which converts our problem into a differential equation, and we can approach it that way. So again, we are focusing on you. We have a student who is borrowing $10,000 to buy a car, and the lender charges him interest rate of 8%. Since you're starting, your interest rate sometimes higher than the market says it is. Assuming that interest is compounded continuously and the borrower makes payments continuously. So these are kind of idealized calculation. At a constant annual rate of K, determine K so that the car is paid off in, say, 5 years. Find how much interest is paid during these 5 years. So remember the formula we had here. I'm just copying that formula down here. We are going to be using that formula. Now we have to understand the situation. In the previous problem, S0 was the original investment, while in this case your investment is a negative amount. S0 is minus B. B is the amount that you're borrowing. So say you are borrowing 10,000. You're not giving the bank 10,000, you're borrowing 10,000. So your S0 is a negative of this amount. Who's your S? Well, the title of car is going to be given to you when you don't owe the bank any money. That means the future amount of your contract is 0. At the moment you don't owe the bank any money, the car is yours. So S at that future date has to be 0. S of t is 0. K is what we want to find. That's a yearly installment you have to pay, and R is given at 8%. So as before, we go ahead and calculate what K is. So you remember the formula for K. So the formula for K, let me write it. We had found in the previous problem, this was S minus S0 exponential of RT over exponential of RT minus 1. This is just a copy of what we had obtained here, so I'm copying that down here. Now to make the letterings so that it will be comfortable to us perhaps for using or remembering, S is going to be 0. In S0 is minus the borrowed amount, so RK becomes R. This becomes minus B, that's going to be just B, exponential of RT, and the denominator is just comfortable exponential of RT minus 1. So to find out how much you have to pay in this problem, 8%, the amount you borrowed, exponential of 8%. We are setting this thing to we are advised to pay it in 5 years. Typically they say don't buy a car if you cannot pay it in 3 years. So let's say 5 years. So this is 5. And same thing, exponential of 0.08 times 5 minus 1. So I invite you to calculate this thing with your calculator, and again go ahead on Desmos, play with this thing, perhaps take a scenario of different R's. Suppose the different banks are giving you different interest rates and you want to know how is that going to influence your installments, and then you can make a graph just like what we did and figure out what the K is going to be, and hopefully you get a nice car. Okay, so this was an application of ordinary differential equation to finance. We had the crucial issue was the following, that ds dt, rate of change of amount, unit of time, is interest rate times the amount plus the constant deposit or withdrawal that is applicable to the case. We solve this thing by appealing to a generic mathematical equation that we have encountered many times before, and we just use that formula for our case, and then we moved forward. Okay, I hope you enjoyed this thing. We are going to have some other applications in mind. I hope you come back for the next lecture. Until the next time, good luck and God bless.